Welcome to today's part of this SPSS methodology. This time with a session on time series and doing prognoses. Well, for this I prepared a simple data set, as can be seen in the background here. So we have a certain number of observations. We can go into the data set here. We see it starts 2000 January, goes up to 2006 December. So we have 7 years, and for each year we have 12 months. Obviously this is time series data because it's only like one variable and we have data for a lot of different points in time. So we first off need to tell SPSS that we're working with time series data, and we have to tell them which type of time series data. This we can do when we go to data and have here define date and time. Click here, and we can select one specific form. With us it's years and month, and it starts in the year 2000, month 1. And here automatically has predefined the periodicity at the higher level, which is here on 12 months. So we can click OK, and he will add a corresponding variable which later on we will indirectly need to work with seasonality effects, which can be found, as well as all the other commands we use, with analyze. Then here we have forecasting. Forecasting, we could either directly go to create traditional models, or if we know that we have some kind of seasonal effects, we could go to seasonal decomposition. Click here. We have to select the variable which contains our information. This is the number. And then we have to select whether we assume it to be multiplicative seasonal effect or an additive one. Here in this case I basically know it's additive, so I can select additive. Else it might make sense to first take a look at a scatter plot for the whole data, or generally a line for the whole data, how this actually looks like. Does this rather fit a typical additive or a typical multiplicative trend, the seasonal effect? Here we will go with additive. Click on OK. He tells me he will add 4 additional variables for this, which then contain the different information regarding the seasonal factors. Then I'm basically done with my preparations. I can return to analyze and forecasting and go to create traditional models. Here I have different ways to actually model this. However, in this case I start with the easy version. I select my numbers as dependent variable, and in this case I do not add any additional independent variables. I could do this, but in this case I'm just going with the basic variables. Then if I go here to method, I see that I have 3 different options: expert modeler, exponential smoothing, and ARIMA. Here in this context we will take a look in particular on exponential smoothing and on ARIMA. So let's start with the exponential smoothing. When I select this, I have to click on criteria and select which type I want to assume here. So this is just a simple version, no trend, no seasonal effects. I could add here trends, and as I before told him prepare some kind of seasonal effect, I also have the possibility to select a seasonal model here. Those were shaded out if I wouldn't have run the seasonal decomposition before. So I could go with additive, click continue. Then I could click OK, but I first want to show a few additional options. So I could go with statistics, and instead of the stationary R-squared I would go with the R-squared in general, giving me an idea how good my prognosis actually is. Then with plots I can add here my fitted values, so not only the forecast and the observed ones, but the fits for the existing time periods as well, and for all of them, or in particular for the forecast, I could generate some kind of confidence interval. Then with output, there's basically nothing important at this moment for us to be done. I could save my predicted values if I want to analyze them further. However, the interesting thing for us here, generally he only predicts one additional value. If you want to have more, you click here, then you enter the last period. So let's go here with one additional year. So in this case you would need to know what your last period was and then enter something which is later than your last period. Then we can click OK and get our results here. And it tells me he runs a Winters additive version. That's the different statistics we get in this context, and in particular here I get as a mean for my R squared 0.981. So we have a fit of around 0.981, so a relatively good model. So we can explain up to 98.1% of the deviation of the dependent variable. It's also summarized again down here. And this is the main result. This shows us here the data we had before. So as we can see, the red line, which is basically in most part overshadowed by our fitted data, the blue one. Those are the time horizon for which we have actual data. We can see, except for those two spikes and this small part here, we have more or less a perfect fit to our data set. Then, starting here, January 07, we have our forecasts. So this is like one forecasting period. We see here we have relatively small confidence intervals in the beginning, and they become increasingly larger. If I would have selected 2 or 3 years, confidence intervals would have steadily grown, because we become way more unsure as the time horizon increases. So this is basically the version to work with exponential smoothing. If I go back, forecasting, create traditional models, to the first selection scheme, and I could also, as I said, use the ARIMA version. ARIMA has two parts: an autoregressive version, AR, that's the first one, an integration part, that's the second one, and then moving averages part, that's the third one. So if I click here, that's also the 3 different things I can specify. And here I can also differentiate between seasonal parts and non-seasonal parts. First off, what does autoregressive difference or integration and moving averages mean? Autoregressive means my dependent today depends on my dependence in the past, and I want to know up to how many past periods do I have to include. So let's go here with one non-seasonal, and let's take 2 seasonal patterns. Difference means I take first differences, second differences, so I take not the values themselves, but the differences between the values. This can be important if I see that my data series itself is not stationary. So if I have a trend, then I can get rid of a linear trend by taking first differences. Can get rid of a quadratic trend by taking second differences. So here I can assume that I have a slight trend, so let's consider difference 1. And moving averages is similar to autoregressive. Here I assume that the error terms from today depend on the error terms of the past. So let's select 1 here as well. Oops. Keep with the non-transformation. Just click on continue. And I get the same results here. I see my R squared in this context is slightly worse. And this results basically here from the fact that he had some problems in the beginning finding the right model parameters. In the end, here I have the same discrepancies as before, here as well, and I see some slight deviations as well. But in the end, looks similar from the forecast than in the other version. This is just, I selected, well, by a gut feeling, the different leg sizes. That's also one of the differences between the ARIMA and the exponential smoothing. Here, with exponential smoothing, I need to know relatively little. Usually I can get way better results with ARIMA if I know more about my data set, if I have done some previous analysis. And I have the big advantage that ARIMA is specifically designed to also work with independent variables, so that I can add like additional explanatory variables here, and then I wouldn't have an ARIMA but an ARIMA X model. So this just as a side note. Basically this is all I wanted to cover at this moment on time series and doing prognoses with time series. I hope you enjoyed listening to it and you learned something from this short session. If you want to see more of this type of videos, feel free to visit the rest of the SPSS methodology. Until then, see you and goodbye.